Hi, my name is Ken, and this is Let's Code a MUD in C++11 Part 9. In the last two parts, we built up our line-oriented connection class for input and handing our input off to the application logic. And in the last part, we looked at R values and standard move to pretty up our constructors and make them behave a little more logically. In this part, we're going to look at the other end of the connection lifecycle. We're going to look at closing connections and how they get dropped out of memory. Let's look at one thing first, which is our server, our accept method here. And one thing you probably have noticed by now is it leaks memory badly. It keeps emplacing new connections into our connection list, but there's nothing actually that causes connections to get pruned from our connection list. Even if they stop trying to read or stop trying to read and write, they just sit there, taking up space in memory. They could even be closed by the client, and they'll still sit there in memory. So we need to address that. We need some mechanism for the connection to signal back to the server that it's over, that it's time to shut down. Let's look at where I want to put that. In the connection base class in our write to socket method, basically I need to find a place where I can determine if we're done reading and writing, whether that be by error or by clean shutdown. So in write to socket, I can definitely determine that we're done writing because we're not going through the more to write dance. But I don't know if we're done reading. So we're going to create a member variable for all of the input classes to signal back to the base class that it's time to shut down. So we'll say if not reading anymore, and at this point we're done writing, go ahead and close up delete self. One thing we need to do here is put a return in here because we're not done writing at this point. If there's more to write, we've just enqueued another async call that's going to get called, so we get a return there. Okay. And what's that delete self going to look like? We can't literally do delete this because then we'll have a dangling reference to it in the list. So we actually need to get it kicked out of the list. So some method in the server class is going to have to exist that allows us to delete a connection. And we'll do it by iterator. Because it's a list, we can delete at any point in the list with constant time complexity. So we'll say there's some connection, and we'll erase that connection. Super, easy, done. Except now each connection needs two additional pieces of information. It needs to know the iterator that it is, where it's sitting in the list, and it also needs to know the location of the server. It needs a reference to the server. This in particular, I'm going to object to a little bit because it's a cyclic dependency. We're saying that the server depends on the connection class, which is going to depend on the server class. And I really, really don't like that. From an architectural point of view, it's ugly. It violates the idea that there should be a hierarchy of dependencies. So you can read down the dependency and say, okay, the server does some stuff and does that stuff by working with the connection, and the connection does some stuff by going back to the server, and it's confusing. It's hard to implement because you need to forward declare classes, and it's also just plain ugly. Okay, so we're not going to do that. We're going to add a level of indirection, which is to say that we are going to use a lambda. And we'll just have the connection execute that lambda, and that way it doesn't need to know what the lambda is doing. So we'll have some connection. In fact, let's have that be an iterator. So let's see, mconnections.end. Oh, I can't. Nope, not connections.end because that's after the end of the list. I could do r begin, but let's just do begin and in place front. There's no difference if we have the newer connections in the front or the end, and then this is a little more readable. So we'll say that there's some set close handler. Right, because what I'd want to do ideally is I'd want to put it in the constructor. I'd want to say, let's put the lambda here, But I need the iterator. I need that connection, and it's not actually in the list yet at this point. It's not going to be in the list until the constructor completes successfully. So in order to use the iterator in the Lambda, I actually have to do it after it's been constructed. And I know that's ugly, that's non-ideal, but you know, it'll look nice when it's done. Okay, so let's create that Lambda. We're going to capture this, and we're also going to capture connection. And we're going to capture it by value. Iterators copy really easily. Think of iterators as no bigger than a pointer. And frequently they're implemented as a pointer. So very easy to capture by value. And what we're going to do here is we're just going to do that mConnections.erase connection. Okay. And while we're here, let's also add a little debugging. Let's see, we have accepting new connection here, but let's actually do that after we've accepted. I also have to close that there. Accepting new connection, total size is connections.size. Okay. And then after we've erased it, let's check that it's gone back down by 1. So we'll say deleting connection, total size is. Okay. And that'll give us a way to debug whether we've done this correctly. All right, so we need that setClose handler method now. But before I move on, I just want to point out already this is looking pretty good because there's kind of a symmetry here. You get to see it's constructed and destructed in the same place, and all that logic is right next to each other. And if we have to change some implementation detail about how, let's say it's not a list class anymore, but it's some custom collection class that we make. If we have to change that here, we can also change how it's deleted from that collection, and the logic is all together. So it has a little bit of symmetry about it that's nice. And yes, it's a Lambda, so it's going to have an unnecessary level of indirection. But to get the logic to all live together and to avoid the cyclic dependency, I can live with it. The indirection is my lowest priority in that situation. All right, so let's go to the connection. So let's actually go to the HPP, and we're going to say we want to have some sort of setClose handler. Some handler type. And we need a place to store it, right? We want to have some member variable close handler equals the handler. So what type is the close handler? We're passing in a lambda. How do we store a lambda? When we talked about lambdas in an earlier episode, we actually said that lambdas are a compiler determined type. So for each lambda, the compiler may make a type for that lambda and then provide you with an object of that type. And that's transparent to the end user. Well, that's nice, but it's not so nice here where I need to know that type. I need to declare it in advance so I can store to it. Well, since you may have lots of different lambdas of lots of different types, and they all need to dispatch dynamically, what you actually need is a sort of container that could contain any callable object. And the standard library in C++11 provides that with the standard function object. So we're going to have some standard function. Actually, it's templated on the arguments of the lambda. So this is going to contain inside it the lambda, and this represents, some sort of callable interface, some sort of least common denominator for lambdas, for function pointers, for even just ordinary classes that implement the parentheses operator. You could store them all in a function. Now, how am I going to pass that in here? Well, one way, we could definitely say, have that standard function of its type and pass it by R value. Unfortunately, this is going to actually create an intermediate standard function. So we have our lambda of whatever type the lambda is. And then when we call setClose handler, this is going to end up, coercing it to a standard function, which we then move into our own object. So rather than have this intermediate standard function, although it'll probably optimize out, the better thing to do, the better pattern for using lambdas as arguments is to just template. So we have some sort of handler type, whether it's a lambda, whether it's another standard function, or whether it's a class with the parentheses operator, and we're going to move it into standard function. So there'll be a move constructor in standard function that will accept the object of the handler type. Now, there's one more tweak I want to make here, which is this might be an object that's movable, or it might be a const object that we have to copy. We need to deal with whether it's copy or move. And we could create two versions of this, although with templates that starts to get hard. So we could create a copy function and a move function. But the standard library actually provides a utility function for this, which is standard forward. And standard forward is copy or move depending on how the template is deduced. And it's kind of complicated how it's implemented under the scenes, but basically it collapses this R value reference into either an R value or an L value reference depending on the type deduction, and then you can standard forward that. So great, we get copy or forward depending on whatever's convenient, or copy or move depending on whatever's convenient. All right, so that's done, but we gotta finish all our logic chains. So we have the M reading. Let's put that up here. Let's M reading will start as true. And then here we're going to have that close handler, and we're going to call it. And then we need to signal at the end of the line-oriented connection that we're done reading. So if we're ever done reading, let's say, just so it looks similar, we'll do it here. Done reading. So if we're still reading, we'll return. Otherwise, we'll call done reading. And what does done reading look like? Right? Because I could have just said M reading equal false. We're done. We're done reading that way. I just changed the variable. But actually, I want to do two things. I want to set reading to false, but I also want to call write to socket, because we might be between writes. There might not be a write yet, and we'd have to wait for the next write to come and to complete before we'd actually close the connection. This way, this at least kicks off an empty write, a zero write that gets that async callback called. Okay. So this is more or less done. I just want to do a couple cleanup things. I want this to be protected, first of all. This doesn't need to be called by anyone who's not a descendant, or not a deriving class. And also, I want to give the class direct access to msocket. And we talked about this in a previous part. But since this is the only thing using the socket now, since we've added that move constructor, we don't actually need to call... We don't need that socket method to exist anymore. Okay, so let's see if this compiles. Okay, it does. And let's try to run it. Okay, and now let's connect. Okay, it says it's accepted the connection. Total size is 1. And then if I quit out of here. Okay, so read encountered an error and it called done reading, and then that caused the connection to get deleted. So there's a lot more things we need to do to handle a graceful shutdown. We need a way for the application logic to feed back in to shutdown. We also want a way for the server to be able to close the connections manually. But all that we're going to do in a later part. So in this part, we got basically client-side connection handled, and the framework to be able to do the rest of our close work. So that'll do it for this part. My name is Ken. I hope you enjoyed watching. This was Let's Code a MUD in C++ 11, Part 9.